Hi guys, welcome back to Puzzle Out. So in this video we will be looking at few basic signals. Now we will be using these signals more often in our coming videos to understand the topic better. So in this video we will be looking at unit step signal, unit impulse signal, unit ramp signal, sinusoidal signal and exponential signal. Let us look at each of these signals in detail. So the first one is the unit step signal. It is called so because it has unit magnitude, that is, the magnitude of the unit step signal is always equal to 1. Also, if the amplitude of the signal is something other than 1, then it is simply called as a step signal. A unit step signal or a step signal is denoted as u of t in continuous time, and it is denoted as u of n in discrete time systems. For a unit step signal, the amplitude is equal to 1 when t is greater than or equal to 0, and 0 amplitude for t less than 0. It is similar for discrete time signals. The only difference is that in the place of t we replace it by n. The unit step signal is represented in the graphical form in the following way. So the graph to the continuous time signal is a straight line parallel to the x-axis with amplitude equal to 1. And for a discrete time signal, the amplitude is always equal to 1 at every value of n. The next type of signal is the ramp signal. It is denoted by r of t for continuous time signals and r of n for discrete time signals. For continuous time signals, the amplitude is equal to t when t is greater than or equal to 0, and the amplitude is 0 when t is less than 0. For discrete time signals, it is the same, but the t is replaced by n. For a unit ramp signal, the slope of the signal is always equal to 1. The graphical representation of unit ramp signal in both continuous and discrete time signals looks as follows. When we closely observe, the ramp signal resembles a y equals to x graph. The next type of signal is the unit impulse signal. For a unit impulse signal, the area under the graph should be equal to 1. If the area is something other than 1, then it is simply an impulse signal. Just like the other signals, it is denoted by del of t for continuous time and del of n for discrete time. The amplitude of the unit impulse signal is equal to 1 at t equals to 0 for continuous time and at n equals to 0 at discrete time. At all other cases, the amplitude is equal to 0. It is represented in the graphical form as follows. Sinusoidal signals. It is denoted by x of t in continuous time and x of n for discrete time. Coming to its functional representation, it can be expressed either in sine or cos. So for continuous time, we can represent x of t as a sine omega t plus theta or a cos omega t plus theta, and in discrete time it is denoted by x of n equals to a cos omega naught t plus phi or a sine omega naught t plus phi. Here omega is the fundamental frequency, a is the amplitude, and theta or phi is the phase difference. In the graphical representation, it traces the shape of a sine or a cos waveform. Exponential signals. It is denoted by x of t and x of n in both continuous and discrete time signals respectively. For a functional representation, in continuous time x of t equals to e power at and in discrete time x of n equals to a power n. So the capital A here represents the amplitude. So in the case of a unit signal, A becomes 1. The exponential graph changes for every value of A. So we consider the graph for different values of A. When A equals to 0, we get a straight line which is parallel to the x-axis. For A greater than 1, we get a rising exponential graph, and for A less than 1, we get a decaying exponential graph. In the same manner, it is represented for discrete time signals. These graphs can also be plotted by substituting random values of A in the given equation.